Okay, so some of you are still here. Yesterday we saw a proof of the KKL here. So we don't need to know what this is because we're going to forget about it today. But just to remind you, so we have the Boolean function from 0, 1, plus minus 1 to the end to plus minus 1. And let's say that it's kind of balanced. So the variance, we assume that the variance was exactly 1, but you can assume that the variance is just balanced from below. Then there must be some variable whose influence is at least log n over n. Okay, this was the KKL theorem. And it implied that if you want to bias the outcomes of the election when everybody else is voting randomly, then it's enough to bribe log n of n over log n of voters. And we don't know whether this is tight, but the KKL theorem itself is tight due to the tribes function. Okay, so we saw all of this yesterday. The proof was kind of mysterious. I tried to demystify it for you using intuition of non sheets. So we considered two cases. The easy case was when the total influence was large, like log n. And then, if you take the average I, then its influence is already log n over n. And the more interesting case was when the total influence is small. Okay, so if the total influence is small, then this means that a lot of the Fourier mass is concentrated on the low degrees. On the other hand, if an influence is small, then this means that if you look at the derivative in the direction, what we call LIF, then most of its mass should lie on high degrees. Yeah, this is because if you're a biased function, then most of your mass lies on high degrees. So we did this calculation for delta functions, and this is true in general. And some of these two things cannot go together. Okay, and there's something quantitative going on here, and if you do the math, then you get log n over n. Yeah, I'm not sure if it's possible to really explain this without going through the math. And we didn't actually go through the math. I told you the solution, log n over n, and we just checked that it actually works. But if you want, you can take it as an exercise and try to balance like the bound you got from the case of high influence with the bound that you get from the case of low influence, and you will get some, you'll see that you get log n over n. Okay, so this statement that if a function is very biased, then most of its Fourier mass is located upstairs. So it's only true for, I think, bounded functions. And the way we expressed it technically was using this level D inequality. Okay, so this is not a sharp level D inequality, you can improve on it. But this is what we'll actually prove. And this means that if you look at the Fourier mass of the function up to level D, then it's, assuming that the total Fourier mass is small, then the Fourier mass up to level D is kind of insignificant compared to everything, because everything is L2 norm of f squared. And if f is very biased, then L2 norm of f cubed is a lot smaller than L2 norm of f squared. So there's something quantitative going on here. So this was the level D inequality. And actually, in a lot of the modern applications of Boolean function analysis, what you really need is this level D inequality. Okay, that's why I'm highlighting it. And this is a weak level D inequality. What you really should be getting is L2 norm of f to the power 4 times some point logarithmic factor. But to get this, I'll mention it today. Okay, and how do you prove this level D inequality? So it follows from something which is maybe more understandable. So it follows from this kind of low degree functions are reasonable. So the degree of the function, just to remind you, is the, if you think of the Fourier expansion as just the multilinear polynomial which agrees with f, then the degree of the function is just the degree of this polynomial. So the idea is that if a function has low degree, then it's kind of well behaved. Okay, so an example of a function which is not well behaved is a delta function, and so it's very, very spiky, has degree n. And this cannot happen if the function has a small degree. So, and one way to measure it is by looking at norms. Now, something that we didn't do yesterday, but we will do now. So we'll actually see what this implies. So we don't need this, but just just so we understand why this is a concentration inequality. Okay, so here is a different way of writing this. And now let's assume that we have some function f. Now this inequality, you don't need the function f to be Boolean or anything. This is true for any low degree function. So let's say, suppose, for simplicity, that f is centered. Okay, then we have Chebyshev's inequality. So it states that the probability that f is larger than some c, so this is at most, let's make it a bit less. And this is at most up to norm squared over c squared. Right, I hope I didn't make a mistake here. So if we think of this L2 norm as, let's say it's 1, then the tail of its distribution indicates at least as fast as 1 over c squared. Yeah, this is Chebyshev's inequality. So whenever the function has variance, then we will have this kind of tail behavior. And now let's see how to use this to improve on this Chebyshev's inequality. So the probability that, yeah, let's say, suppose f has degree d, and we think of d as, let's say, a constant or something small. And I actually need this, so okay, then the probability that x greater than c, and then we're going to do the same proof as proof of Chebyshev's inequality. So the probability that f of x to the 4 is c to the 4, which is at most the expectation of f to the 4 over c to the 4, which is at most, yeah, so it's written here. It's 9 to the d f2 to the 4 over c to the 4. Okay, so the way to think about this, let's say we normalize so that the variance is 1. Okay, so if the variance is 1, then this would be one over c squared, and here we'll get nine to the d over c to the 4. Okay, so if we also think of d as constant, then this shows that actually the tails are at most like 1 over c to the 4, which is a faster decay. Okay, so why am I saying all this? So the point here is that this inequality here, this is a kind of a concentration inequality. It states that the function f is concentrated. Yeah, and actually, so here we show 1 over c to the 4, but if you use general hyperconductivity, which we will mention later on today, then you get exponential tails. So the truth is, if d is constant, you get exponentially decaying tails. Where instead of, so if d is equal to 1, then the exponent will be e to the minus x squared. Instead, it would be e to the minus x to the power 2 over d. Okay, so it will be exponential, but not in c, but in some polynomial in c. This is using a similar calculation. And actually, people doing large deviations, then this kind of tail bounds are equivalent in some sense to this kind of moment bounds. So if you widen your net enough, then you can connect to also large deviation theory. But we're not going to do that. Okay, so this was just a quick comment about why the correct way to think about this inequality is as some kind of concentration inequality. And it also implies anti-concentration, but we won't show it. Okay, questions? Okay, so our goal today is to prove this inequality. And the proof of this inequality will follow from something known as hypercontractivity. Okay, so I'll first tell you what does this term mean, and then we'll discuss a bit, how to prove it, and then we'll see maybe a few more applications. Okay, so there will be some operator T which maps functions to functions. So given a function f from plus minus 1 to the n to r, you will define or rather, we'll define T f, which will be another function from plus minus 1 to the n to r, such that T is a linear operator. Okay, so T is some linear operator which takes a function and returns a smooth version of the same function. So it just smoothens its bumps a bit somehow. Yeah, it's going to be some kind of local averaging operator. So at each point, we compute some kind of average over some kind of soft neighborhood. We'll define it exactly, but that's for now. So this will be a bit abstract, but we will make it super concrete in a moment. Okay, so we say that T is contracted for LP, and you can really choose any norm here. If for all f, TF P is at most FP. Okay, so this is an operator which it contracts norm. Okay, and if you've ever seen Banach's fixed point theorem or one of these fixed point theorems, then there we need I guess a strictly contractive operator, and we can show that it has a fixed point. Okay, so this is something that somehow rearranges mass in a way that makes the function smoother. Okay, so hyperconductivity is this very strange phenomenon. Yeah, so there is some P larger than Q, such that for all f, TF P is at most F Q. Okay, so if you remember yesterday, we said that the LP norms, they're monotone in P. So in general, you would expect the P norm to be larger. It's always at least as large as the Q norm. And it can be exponentially larger. If you take a delta function, so not exponentially, but I guess going larger. So if you take a delta function, then you can do the computation. So this will be 1 over 2 to the n to the power of 1 over q, and this will be 1 over 2 to the n to the power of 1 over p, which is a lot larger. Okay, so if we didn't have this operator here, then there's no way that this kind of inequality is going to hold. So this is some kind of magic. It's something which is unexpected. And sometimes we also allow a constant here, but actually because of the way that the proof works, then if we did have this constant, then it would be very bad. So we won't be able to prove it. So the best constant here, the most reasonable constant here is 1. Okay, and well, you can imagine that we will take p equal to 4 and q equal to 2, and we will somehow derive this from this sort of statement. Okay, so this is what the term hyperconductivity means. My understanding is that this hyperconductivity, it came up naturally, whatever that means, in functional analysis. Maybe people were trying to solve differential equations, and then they need to show that the solution exists, and somehow they need to look at norms, and this thing popped out, maybe. Yeah, so for us, it's like prehistory, and this is something that the people of KTL, they came up with and they saw in the literature, and now we all forgot about it. Okay, so this hyperdestructive inequality that I'm going to describe was first attributed to somebody called Beckner, William Beckner. And then it was found out that actually somebody else called Bonamy proved it a few years back. And then they found that also somebody called Leonard Gross proved it. I'm not sure, like maybe it was in the middle. Anyway, now it's called Bonamy lemma, but I guess the PC term is hyperconductivity. Then you don't offend anybody. Yeah, so it's somehow this sort of statement. It's common enough, it's natural enough that many different people found themselves proving it. Okay, so as we will see, the proof is some sort of induction. So it will be very simple, really, the proof of this thing. And this is the one induction that you need for most results in Boolean function analysis. Okay, so many of these results, the way to think about them. So often we want some result which is dimension independent. And the way that we're going to get it is by doing some induction on the dimension. But we don't want to do the induction each and every time because these inductions are tricky. So what we're going to do is we're going to reduce everything into this single induction, which is lies in the proof of this hyperconductivity. Okay, so when we proved KKL, there was no induction. Okay, the induction was hidden in the proof of this thing, which will follow directly from this hyperconductivity. There are some other inequalities in Boolean function analysis which are less useful, like there's something called Talagan's inequality, which was, I guess, useful for Talagan, but I've never seen any other application. And then you need to do the induction from scratch. But usually it's just a reduction to this hyperconductivity or to one of its corollaries. There's also something called reverse hyperconductivity, which is, I guess, maybe a little bit different. So another induction. Yeah, and that's part of the mystery of the subject, because there's this one tool that you're supposed to use somehow, and you just need to figure out how. So you see many examples, and yeah, maybe it's similar to regularity and other parts of combinatorics, where this is the tool that you need to somehow use if you want your proof to be non-trivial, and you just need to figure out why. Okay, so this was a lot of theoretical talk. So now we'll get more concrete. So I'll define this operator T for you. So actually, it's going to have a parameter rho. Okay, I'm going to do it in two steps. Yeah, there's some relation that I will mention to random walks. And then these operators TO, they form a semigroup. Okay, but we will not use this point of view here. They just, yeah, all of these things are connected to several different areas of math, and like the terminology is a little bit different, and the way to look at things is a little bit different. So I will mention some of these keywords, but we will do it from a very particular perspective. Okay, so for every x in plus minus 1 to the n, we will define a distribution and rho. So when we get to p bias analysis, then it will be an issue because rho and p, they look the same. But for now, it's not an issue, so it's fine. And rho x, which is a distribution on plus minus 1 to the n. So you should think of it as adding some noise to this point x. And then we define p rho of f at the point x is the expected value of or y samples according to this new rho of x, f of y. Okay, so y is this kind of noisy version of x, and p of f at the point x is an average over this neighborhood of x. The values of f over the neighborhood of x. Okay, and because of the way that we define n of x, then it will be obvious that this zero is contracted with respect to any norm. We'll see this. And then we will show that it's actually hypercontracted for an appropriate value of rho, depending on P and Q. Okay, but I still need to tell you what this n rho is. So n rho of x at the point I is xi with probability 1 plus rho over 2 and minus xi with probability 1 minus rho over 2. Or an equivalent definition, so it's xi with probability rho, and it's random with probability 1 minus rho. Okay, so both of these definitions, they only make sense when rho is between, I guess this makes sense when rho is between 0 and 1, and this makes sense when it's between minus 1 and 1. But we will see how to extend this definition for any real and even complex rho. So in functional analysis, they have this thing called complex interpolation, where it's important that this rho is complex. We won't need this. We don't like complex numbers. For us, rho will be enough. Okay, so maybe it's not obvious that these two definitions are the same. Okay, so random I just mean half-half. Okay, so let's take this definition. So what is the probability that n or xi is equal to minus xi? So this can only happen if we are in this part, and if we sample minus xi. So the probability is 1 minus rho over 2. And then the complement is rho plus 1 minus rho over 2, which is 1 plus rho over 2. Okay, so these two definitions are the same. But this one will generalize better when we do the p-bias Fourier analysis. Okay, and now let's take some extreme examples. So what is n1 of x? X, okay. What is n minus 1 of x? No, we'll also do 0. Okay, let's do 0 first. What's n0 of x? Random. Completely random. What's n minus 1 of x? It's a bit less useful.
Minus.
Okay. So what's T1 of f?
The expectation of f.
Okay, so at the point x, it's expectation of f of y when y is chosen according to n1 of x. But n1 of x is just x. So it's expectation of f of y when y is equal to x. So it's f of x. So T1 f is just f. Okay, and what's T0 of f? Right, this is the constant function, which is the expectation of f. So from the semi-group perspective, you can imagine that this rho, it goes down from 1 to 0, so it has to go down exponentially, but let's not worry about this. And you start with the function f, and you eventually you spread the mass out, and eventually you get to a constant function where the constant is the expectation of f. Okay, so this is kind of so what's happening here, I'll say it again later, is that there's this continuous time random walk, okay, which it starts at the point x, and we stop it after some time. If we stop it at time 0, then it's just a function f. If we stop it at time infinity, then now it's completely spread over the all the points equally, so we get the expectation of f. And if we stop it in the middle, then we'll get this T of f for some y in the middle. Yeah, this is the random walk point of view. And sometimes to understand these things, then we consider this dynamic process. This is called the semigroup method, and it involves a lot of calculation. So we won't give any example because, yeah, it's a lot of calculation. Okay. So what we will do now is first, I want to show that this TO thing is contractive. Okay, at least when rho is between -1 and 1, contractive for any norm. And then we will compute the Fourier expansion of T rho f. And then we will state hypercontractivity, we will deduce this thing, and we will prove hypercontractivity. And then we'll continue from there. So if you're wondering, that's what I have. If this, we erase these things. Okay, so there's a claim. T rho is contractive for any norm. And here we assume that rho is at most 1 in absolute value. So if you care, this will also be true for complex rho, probably. Just forget about it. Okay, so why is this the case? So we observe that n rho of x is the same thing, it's the same distribution as x times n rho of the point 1. Yes, I need to check it. So n of the point 1, it's 1 in each coordinate with probability 1 plus rho over 2, and otherwise it's -1. And when you multiply it by x, it's the same thing as the definition there. Okay, so P rho f of x is expectation over z, which is n rho 1 of f of x times z. Okay, now we define f z of x. This is going to be f of x times z. Okay, so this is just a shifted version of f. Okay, so then T rho f is the expectation over z, which is sampled according to nu rho of 1 of fz. Okay, so it's just an average of many shifted versions of f. Okay, so we're just like switching order of summation or something. Okay, now you take any norm. So not any norm, so any norm shift invariance. So we'll see what shift invariant is. Let's think about LP norms, but it's true in greater general. Okay, so the norm of T rho f. So this is the norm of this taken over z with some probability of ft. And now if we apply the triangular inequality, which is the defining property of norms, then this is at most the norm of f. Now a norm is I guess called shift invariant, but maybe call it translation invariant. Okay, so let's write it here. So a norm is translation invariant if the norm of fb is equal to the norm of x. Okay, so it's invariant under translations. So example, the LP norm. Okay, so the LP norm is just the expected value of the function to the power p, up to, let's say, the LP norm to the power p. And when we do this translation, then it's just a rearrangement. Because in the uniform distribution is itself translation invariant, then it will be the same. It's just changing the order of summation. Okay, so the LP norm is translation invariant. Okay. So for a translation invariant norm, then all of these things are equal to the norm of f. So this is just the norm of f. And so this kind of averaging operator, it can only decrease norms. Okay, so these we call this the noise operator. So these noise operators are inherently contracted, just because they kind of take the function and they look at some of its translations and they do some kind of average, and this can only make the function tamer. Okay, it's true with respect to any translation invariant norm. And the surprising thing is that it's not only contracted, but also hyper-contracted for some P and Q and for the appropriate law. Okay, so questions about this definition of P law, this contractivity.
That's the thing. And this definition, be generalized to P bias stated.
Yeah, so we'll see that I guess probably tomorrow. But just as a preview, so and you can do a definition this way, but maybe it's not so clear how to define these things. So what is important in the p-bias case? So the p-bias setting is the probability of sampling xi equal to 1 is going to be the parameter p. This is the p-bias distribution mu p, in case you might have heard about this. And it's important that if x is sampled according to mu p, then the noisy version n of x is also sampled according to, has the same distribution. So you need to define this thing somehow so that it actually works out. And maybe it's not so clear to do it, but if you define it this way, then this will automatically be the case. So now if x is sampled according to mu p, with probability we keep it, and otherwise we resample it according to mu p, and then automatically this will be distributed mu p. Yeah, and also this gives you the right parameterization. So we will see it tomorrow. Yeah, you can also generalize it to other domains. So, yeah, like I said, it's kind of, there is hidden here a continuous time Markov chain. So I don't know if you've ever seen continuous time Markov chains. So I'm not sure, like, probably probabilists know about these things. So it's like a Markov chain, but there are these exponential clocks. So at each epsilon point in time, there is some c times epsilon probability of a jump. Okay. And in this case, c is equal to 1, and a jump was just a move on the hypercube graph. And if you stop it at time half ln 1 over rho, then this is exactly the same as this n rho. So you start at x and you do this continuous time walk. Yeah. And you stop it at some time which depends on rho, then this will have the same distribution as n rho. Yeah, so this is the correct way to look at it. And now you can define this random walk on whatever graph that you want, as long as you have this Markov chain on it. Okay, so maybe you want to do, you're doing a random walk on the symmetric group, and each time you jump, then you apply transposition. Okay, so this is how to define this entire setup to other domains. But it turns out that the salient properties of this TRO are actually something about eigenvalues, which we'll see in a bit. So we want the eigenvalues to not drop too quickly. We'll see it in a bit. And this level inequality, or rather stronger versions of this level inequality. So in many modern applications, we don't care about this operator TRO coming from random walks. We just care about this property and about this other property that means that kind of TRO doesn't kill the function too much. Yeah, so you can satisfy this inequality automatically by just taking okay, we haven't seen it, but yeah, so the way to derive this kind of inequalities is from this hypercontractivity, and we will be able to satisfy hypercontractivity by setting T to be the T0 operation. But this is not interesting. So we need to find some random walk operator which satisfies hypercontractivity and also doesn't kill the function in a particular sense, which we will be able to express in a moment. And these are the salient properties of this TRO, so it doesn't really have to come from a random walk. And in the modern applications, you define it in some more complicated way, where it's not a random walk operator, but it satisfies all the properties. Okay, so maybe at this point, it's impossible for you to understand what I just said, but we will get to it in a bit. Okay, then I will repeat everything and you will understand a bit more. Okay, so just because somebody asked. Okay, so if you feel lost, then you can jump right back, because now we're going to get concrete again. Okay, so what we're going to do now is we're going to see the effect of this TRO operator on the Fourier expansion. And this will allow us to prove this given hyperconductivity, which I haven't yet stated, but I will state in a bit. Okay, so we want to know, given the Fourier expansion of f, what is the Fourier expansion of TRO f? Okay, now because this TRO operator is linear, so this is clear from the definition, because it was the expectation of something. And then it's enough to know what is its effect on the Fourier characters. Okay, and because it's defined on coordinates independently, it's actually enough to know what is its effect on just xi. Okay, so we just need to compute TRO of xi. Okay, so TRO of xi, this is the expected value of yi, where yi has the distribution and rho of xi. Okay, and now we will do this calculation in two ways, according to the two definitions. Just so, because according to the first definition, maybe it's a little bit simpler, but we will need the second calculation in the p-bias setting, so we'll do it twice. Yeah, so calculation one. So with probability 1 plus rho over 2, this is xi. And with probability 1 minus rho over 2, it's minus xi. Okay, so what do you get when you add these two things?
Rho x.
Oh, xi. Okay, and if we do it the other way, so now we use the second definition and we will call this zi. So then with probability rho, it's equal to xi. And with probability 1 minus rho, it's the expected value of zi. but the expected value of Zi is 0. Okay, so this is also rho of xi. Okay, so this wasn't a good calculation. This rho is the eigenvalue I was discussing. We'll see it in a moment. Okay, and now what is T rho of ES? So I just remind you that this is T rho of product I in S xi. So this is expectation of y according to n rho x of ES y, which is the expectation, this y of the product ys to yi. Now, because everything is independent, then this is the same as the product I and S of expectation of yi, which is the product I and S rho times xi, which is the rho to the power s, product of the xi, which is rho to the power s, ts. Okay, so I mean, this is really a very easy calculation. Just everything is applicative because everything is independent. Okay, so the effect on xi is multiplying it by rho, and the effect on xi xj is multiplying it by rho squared. The effect on ts in general is multiplying it by rho to the power s. Okay, this is a very easy calculation. And this means that T rho of F, this is sum over S, of the power S, F has S, T is, or in other words, if you look at the Fourier expansion of F at S, the coefficient, then this is O to the S, F hat of S. Okay, so this acts like a kind of soft low-pass filter for the engineers here. So we multiply the level D of the Fourier expansion, which is composed of the sets S of size D. So we multiply level D by a factor of rho to the D. So we think of rho usually between 0 and 1. So as D gets larger, so this rho to the D gets smaller. Okay, so this has the effect, it doesn't change at all level 0. And as we increase the levels, then it kind of kills the high levels almost all the way to 0. Yeah, so usually we think of this rho as constant, but n is increasing. So the high levels, they really get dropped down to almost 0. But the low levels are only slightly affected. Yeah, and we call these rho to the s, these are the eigenvalues. Now I'm putting it in quotes, but actually they are the eigenvalues of this operator. So you can see that the eigenfunctions of this operator are just these Fourier characters. And this rho to the s are actually the eigenvalues. Okay, so if you think of this thing as just a linear operator, then it has eigenvalues and eigenvectors. In this case, we call them eigenfunctions. And these eigenspaces correspond to the levels of the Fourier expansion, and the eigenvalues are this rho to the d. Okay, so what we care about this operator is mainly these eigenvalues, and we will see very shortly why. Okay, so now finally we can prove this thing, and you will see the proof is not very hard. So now that we have this formula for T rho, then first of all, you can see this semigroup property that T rho 1, T rho 2 is T rho 1 rho 2, so let's write it. This is the semigroup property. So T rho 1, T rho 2 is the same as T rho 1 rho 2, and in particular, the inverse of T rho is T rho minus 1. Okay, now it cannot be that both rho and its inverse are between minus 1 and 1. So one of them, you cannot really define it the way we define it here. But using this definition, this T rho f makes sense for any rho, even complex rho. Okay, so maybe it no longer has any probabilistic meaning, but it has some, we can compute it. Maybe it's meaningless, but we can compute it. Yeah, but if you want, then if you look at something like T squared 3, then this is the inverse of something that does have a probabilistic meaning. Okay, and now can state, let's state it here. So this is going to follow from T1 over square root 3 F4 is at most F2. So this is L4, L2 hyperconductivity. Okay, so this is this Bonomi's lemma that we are actually going to prove by induction. And this will imply this thing. And we'll see it now. Okay, so we want to get a bound on F4 squared. And we want to use hyperconductivity, but we don't have any T's here. So we need to somehow introduce them. Okay, so how do we do that? So we would like to somehow apply this hypercontractive statement that we will prove next. But how do we introduce this noise operator into this, which doesn't involve any kind of noise? Right, so this is equal to T1 over square root 3, T square root 3, F4 squared. Okay, so we just apply this noise operator and its inverse. Okay, and this is at most hyperconductivity. T square root 3 F2 squared. Okay, and this is sum over S of square root 3 to the S F hat of S squared. Okay, so we multiply the S's Fourier coefficient by square root 3 to the size of S. This will give us the Fourier coefficients of T squared 3F. And then we have to square them and sum over everything. And this is 3 to the S F hat of S squared. Okay, now because F has degree at most degree of F, then we can bound this 3 to the power S. Okay, it's at most 3 to the degree of F. So this is at most 3 to the degree of F times f of f squared, which is root of the graph f, f2 squared, okay, which is what we promised. Okay, so by applying this noise operator and its inverse, then this immediately gives us this thing. Okay, so questions about that?
If we consider T illustrate as X for specific X, can we also write down as before, somehow randomly sampling in expectation?
Yeah, so this is like a global property of the function f. So I'm not sure you can say what happened at that particular x.
So it's only possible when law is in the range of 1 and minus.
Ah, okay, so that's what you're asking. Yeah, so this T rho is only contractive when rho is between -1 and 1, and there's no reason to expect it to be hypercontractive when rho is large. This will be strange. I think even if you just consider linear functions like the function x1, then probably you can already see that it's not going to be anything if rho is larger than 1. Yeah, and we actually know the optimal rho for any two norms, so I'll write it in the end. Yeah, so now I can explain this vague stuff I talked about earlier. So in application, it turns out that what you really care about is the level D inequality. Okay, and the level D inequality follows from this kind of moment bound. And this kind of moment bound, it follows by combining a hypercontractive statement with a lower bound on the eigenvalues of this operator for low degree functions. Okay, so if we look what's happening here, then where did this 3 to the degree of f come from? This is 1 over square root 3 to the d squared. And this 1 over square root 3 to the d, this is the minimal eigenvalue of any eigenfunction of degree at most d. Okay, so for this entire thing to work, you need both a hypercontractive noise operator. So the difference between 4 and the 2 will give you here a power which is larger than 2. Yeah, this is how you get a saving. And to get this factor, this is connected to these eigenvalues. So if the eigenvalues they decay too fast, then whatever you get here will be too large and not be useful. So if you need to use the hypercontractivity in some other setup, then these are the only two properties that you need. You need some sort of hypercontractivity and you need a bound on the eigenvalues. Okay, and in some more general situations, which we will not go through today, then you somehow construct this noise operator in various ways. And these are the only two properties that you need. So this connection to random walks that I explained, this is maybe how people used to think about it, but you don't actually need it. Okay, so if you read some of the modern papers on the subject, then they don't bother explaining it, or maybe they do explain it very quickly, but this is what's really happening there. So they're constructing these noise operators, and they only need these two properties, that the noise operator is hypercontractive, and that the eigenvalues, they don't decay too fast. And this is how you get this level D inequality, which is what we actually need in this application to extremal combinatorics. Okay, so we really won't have time to get into any of this. Instead, I want to talk next about this global hypercontractivity, which is also part of this new stuff. Yeah.
I have a question. We start with a non-product measure like a Gibbs measure what we have a similar noise operator on.
Yeah, so I think for the Gibbs measure, it's very natural. So it's also like a continuous time Markov chain. And when you resample the sampleability according to the marginal distribution. Yeah, so these things are studied in classical probability theory. So they also care about this convergence of Markov chains. Okay, so one thing which I didn't mention so far, if you just look at the eigenvalues, then this measures convergence in L2 of the Markov chain. Okay, so now we're back into the Markov chain picture. So fast mixing Markov chains, it's often defined by looking at the spectral gap. The spectral gap corresponds to the maximal eigenvalue, which does not correspond to the stationary distribution. Okay, so here it will be rho. Okay, so if this rho is bounded away from 1, then the Markov chain has a spectral gap, so you have fast mixing in L2. But in Markov chain theory, what we really want is fast mixing in L1. Okay, in total variation distance. So one way is to get it is from fast mixing in L2, which is spectral gap, but you lose a lot this way. Another one is by looking at mixing in KL divergence. Okay, some other notion. Mixing, which corresponds to something called Sobolev inequality, which is equivalent to hyperconductivity in some sense. Okay, but it's a stronger property. So there are some Markov chains which they have a spectral gap, but they don't have this kind of mixing in KL. Okay, but if you do have this mixing in KL, then you get a better bound on the mixing in total variation distance. And for this reason, then these people doing probability theory, like using models, whatever, they want to prove convergence in L1, and they want to prove on spectral gap, so they care about this log-Sobolev inequality. So then I would expect them to really have proved log-Sobolev inequality for these models, which is equivalent to hyperconductivity. Okay, so if you couldn't follow, then it's okay, we can forget about it. But anyway, this hyperconductivity is connected to something in convergence of Markov chain theory. And if you couldn't follow, then this is okay, because now we're going to forget it and go on to the proof of this hyperconductive statement. But first, are there any more questions?
What was the keyword that you mentioned? No, something.
Log-Sobolev, yeah. Yeah, so the story here, there is something called Sobolev inequality in functional analysis, which might or might not be related to Sobolev spaces. Yeah, I'm not a functional analysis person, so I don't know. And this Sobolev inequality, there is a different version where you put some logs somewhere, and it's called the log-Sobolev inequality. And it turns out that this log-Sobolev inequality is actually equivalent to a bunch of other stuff. Okay, so this is the picture. We in Boolean function analysis are kind of users of these things, so I don't know anything about functional analysis, like Sobolev spaces. I just know the name, but this is somehow all related. And maybe if we knew more about functional analysis, it would make us better Boolean function analysts. Yeah, but these are the keywords if you want to look it up later. Okay, so I think it is enough of this abstract stuff. And now we're going to get concrete again. So if you lost focus, you can try to focus again. And now we're going to prove this hyperconductivity. By induction, the proof will be quite short. So it's actually an easy proof. Yeah, so we will need several boards, but this is not because the proof is long, it's just because the equations are long. And so to complete the proof of the KKL inequality, we reduce everything to prove this Bonamide lemma. So let's state it. Bonamide lemma, which is also L4, L2 hyperconductivity. So P rho F 4 to the 4 is at most f, so t1 over x squared 3. F 4 to the 4 is most f 2 to the 4. This is true for every function f on any dimension hypercube. Then we are going to prove it by induction. So this is a proof. Let's see the induction on n. There's at least one hypercontractive inequality where the induction is not on n, but on the degree of the function. But this will be an induction on n. Okay, so base case n equal to 0. Okay, when n is equal to 0, then f is just a constant, and this operator, it has no effect. And also all of the norms are the same because they're just 1 point. Okay, so in this case, they're equal. Yeah, so in this case, t1 over square root 3 f4 to the 4 is equal to f2 to the 4. Yeah, just because all these things are equal to the unique value of f, absolute value to the power 4. Okay, so the base case is kind of boring. The real base case is n equals 1, but we want to do the proof this way, so you won't see it. Okay, now the inductive step. So we assume statement for n, and we prove it for n plus 1. And the idea is to decompose the function f into two functions on a lower dimensional space. There are kind of two ways of doing it. Either you substitute the coordinate, or we do something a bit different. So we write f of x1 to xn plus 1. This is g of x1 xn plus xn plus 1 h of x1 xn. So we think of this f, of the Fourier expansion of f, as just a multilinear polynomial. Yes, a polynomial where no variable is squared. And we just separate it into the part not mentioning xn plus 1 and the part mentioning xn plus 1. Yeah, but you can also do it completely. So g is going to be sum of s subset of n f hat s ds, and h going to be s subset of n f hat of s plus n plus 1 ps. Okay, and the induction hypothesis is that t1 over square root 3 g 4 to the 4 is at most g 2 to the 4, and the same for h. Okay, so far we haven't done anything. Right? Okay, so we want to bound P1/√3 F 4 to the 4, which is expectation of P1/√3 F to the 4. Okay, now what's T1/√3F? Okay, so I'll write it here. So if you look at this at the yellow formula, then when we apply this T1/√3, it's like multiplying every variable by rho. Where rho is 1/√3. Okay, so if you do it, then you get this is T1/√3 G plus xn plus 1/√3 T1/√3 H. So again, when we apply T1/√3, this is like multiplying each of the inputs by 1/√3. And if you substitute it in this yellow equation, and when you do this for the G part, then you just get T1/3 G. You do it on the other summand, then you get xn plus 1/√3 times T1/√3 of H. Okay, so this is what we get here. And you can also see it if you want by just expanding everything, looking at the Fourier expansion. Okay, so this is the expected value of T1/√3 G plus xn plus 1/√3 T1/√3 H to the 4. Okay, and what we're going to do now, we're just going to apply the binomial theorem, and we will get 5 different terms. Okay, so this will be equal to expectation of, this is the most difficult part of the proof. I actually have to write everything. E to the power of 4 plus 4/√3 expectation of xn plus 1 expectation of T1/√3 G to the power 3 T1/√3 H. So I'm separating it according to the first n variables and n plus 1. Okay, plus 6/3 expectation of x n plus 1 squared. Expectation T1/√3 G squared. T1/√3 H squared plus 4/√3 expectation of xn plus 1 cubed. Okay, almost done. Okay, so like I said, this was the difficult part of the proof, just writing everything out. Okay, so we have 5 terms, but actually only 3 of them are non-zero. Okay, so what is expectation of x1? Xn plus 1?
0.
0. Okay, so I wrote all this mess, but this is just 0. What is the expectation of xn plus 1 cubed?
1. 0.
So it's plus 1 with probability half, minus 1 with probability half. It's also 0. So this is also, we can forget about it. Okay, what is the expectation of xn plus 1 squared?
1.
1. And what is the expectation of xn plus 1 to the power 4? 4. Okay. So I wrote all this mess, but actually we don't need it. Yeah, so we only have 3 terms left, so let's write them. So this is expectation of t1 over square root 3 g to the power 4 plus 2 expectation of t1 over square root 3 g squared t1 over square root 3 h squared plus 1 over 9 expectation of t1 over square root 3 h to the 4. Okay, so I chose 1 over square root 3 so that I get 2 here. It's a spoiler. Okay, so now it looks a lot better. So this, we know, this is just our induction hypothesis. This is at most g to the 4. And this is at most h2 to the 4. Okay, so this is, there's this 1 over 9, but it's at most 1. So this 1 over 9 doesn't help us. Okay, so now we just have to deal with this term. Okay, so this term, we can apply the Cauchy-Schwarz inequality, which is the only inequality that you ever used, right? So this is most square root of notation of P1 over square root 3 g to the 4 times notation of P1 over square root 3 h to the 4. So this is Cauchy-Schwarz, which is at most g2 squared times h2 squared. This is the induction hypothesis. Okay, so we applied the Cauchy-Schwarz inequality to get into something which we can bound using the induction hypothesis. So now we summarize everything. And what we got that this is at most g into the 4 plus y g2 squared h2 squared plus h to the 4, which is g2 squared plus h2 squared squared. Okay, but what is g22 squared? So ultimum of g squared, this is the sum of all the squares of the Fourier coefficients of g. And this is the sum of all the Fourier coefficients of h. Now, if you look at the definition, if we sum over all the squares of Fourier coefficients of g and of h, we just get the sum of the squares of all the Fourier coefficients of f. Okay, so this is F2 to the 2 squared, which is F2 to the 4th. Okay, which is what we had to prove. And so this is another one of these proofs that write themselves. So we only had to do two things for this proof. So we had to decide how to do the induction. Yeah, so like I said, the other reasonable way to do the induction is to fix one of the coordinates to both possible values. But here it turns out that this is a better idea. And then we had to apply the very sophisticated Cauchy-Schwarz inequality, yeah, which is usually the first thing you have to try anyway. Okay, so this is the entire proof of hyperconductivity. So you can see it's not very scary. It's just an induction, and kind of actually the proof is very elegant. Okay, so with this induction, we can prove this moment comparison with this an easy calculation. And this implies this level D inequality, which is what we had to do to prove the KKL theorem. So this completes what we started yesterday. Okay, so questions about all of this?
I have
Yeah.
a question. Can we find other kinds of linear operators which are which satisfy the hyperconductivity but does not look like the theorem?
Yeah, so people in coding theory, or one particular person for MIT, was interested in the operator which, instead of changing, so T rho, it flips rho n of the coordinates, so sorry, 1 plus 1 minus over 2 n of the coordinates in expectation, some fraction of the coordinates in expectation. And this guy, he was interested in the operator which flips exactly this number of coordinates. So you choose a subset of the coordinates of size exactly 1 minus over 2 times n, and you flip them. And for some reason, this made sense to him from a coding theory perspective. And he wanted to know whether this operator is also hypercontracted. And he wrote like a paper with 20, 30 pages, and he proved that this is hypercontracted. Yeah, so this is one example. The other examples is these things that come from applications where what happens there is you have one domain which you know is hypercontracted, and you want to prove that a different domain is hypercontracted by reduction. And when you do this reduction, then you get these funny node operators, because they somehow, the node operator itself, it contains as part of it this reduction. Okay, so it's a bit vague, but if you're interested, you can talk to me later. And then we get these funny node operators, which they don't come from random walks.
So, and do you have any kind of standard to judging which hyperconductivity operator is better?
Yeah, so from the point of view of applications to extreme combinatorics, then you just need this level D inequality. Okay, so if you want to bound the size of product-free sets in groups, or sets without arithmetic progressions, or if you want to say that a set whose square is everything needs to be at least so big, a set whose square is almost uniform has to be so big. So all of these statements, eventually they're reduced to some kind of level D inequality. And you just need a level D inequality. You don't care how you get it. So you just need some noise operator which satisfies some kind of hyperconductivity, and the eigenvalues, they don't decay too fast. And if you get better parameters for this noise operator, then you will get a better level D inequality, and so a better statement in the end.
So it seems like we only care about the existence of this theorem.
Yeah. But if you're doing, if you care about convergence of Markov chains, then actually you have a random walk in mind already, and you want to understand it. And then it's the opposite. Then this noise operator comes to you from somewhere else, and you just want to analyze it. So if that's what you're doing, if you want to understand the convergence into the Ising distribution, then you're given the noise operator, and you want to know its hypercontractive properties. Yeah, other questions?
Why is this proof 30 pages?
No, so you should really be asking why it is not 40 pages. So there's all of these calculations which are kind of missing. It's a matter of style. So it's the Russian style, where the story is that in Russia, paper was expensive. So the journals, they didn't contain any of the proofs. They just contained the statements. And then they made up the story that, yeah, we don't want to ruin it for future mathematicians by looking at the proof. So we just want to say what is true, and you can try to prove it yourself. But I think the real reason is because paper was expensive. So it was written in this style. So there were many statements which took a few lines to verify. And yeah, they all were correct. So it's this kind of like a Bergen style paper where you have a bunch of statements that you can follow and everything is true, but you don't see what's going on. So I think you had to consider different cases depending on the value of the small parameter, and you had slightly different proofs. It's very technical. Yeah, so this proof is very simple, but the general hyperconductivity is more technical. So by now, like, people worked hard on it, and we have short proofs. But still, some calculators are involved. Yeah, so I had to actually refer you this paper, so that's why I know that it should have been longer. Yeah. But now that we know that it's true, we don't need to know the proof. It's already proven true. Yeah, so to finish today, I will very briefly mention general hyperconductivity because it's actually quite useful. So yeah, let's erase this. Okay, so you can ask, given P, which is at least Q, which is at least 1. So it's going to be at least 1 because LP is a norm only when P is at least 1. For which one do we have P rho F E is at most F Q. And so this is to answer that question. Okay. So this is definitely true for rho, which is equal to 0. Okay, but it's not very interesting. So as it turns out, so this holds for all F. If and only if this rho is at most square root of, so if I don't get it wrong, Q minus 1 over P minus 1. Okay, so if P is 4 and Q is 2, then you get 1 over square root 3. Okay, so to check that this is the optimal parameter, this is easy. So you just look at the n equals 1, and you look at functions which are like 1 plus epsilon x, and you'll get this. So this is how to get this value. And then to prove this, so it's in 2 steps. So step 1 is the base case, n equals 1, which is known as a 2-point inequality. So it's called a 2-point inequality because the function 0 plus minus 1 to the 1 has 2 points. So it's some inequality involving 2 free variables. And actually, because it's homogeneous, you can reduce it to 1. So just it's some inequality in one real variable. So you can ask me, how hard is it to prove it? So it's not very fun, but by now we have short proofs, which are like, I think, 2 pages. So in Ryan O'Donnell's book, I think he proves it in 2 pages, this 2-page inequality. And then you do induction. induction, or sometimes it's called tensorization. Tensorization, which is just a fancy name for induction. So the thing is that everything here is defined by tensorizing. So you get the Fourier basis by taking a Fourier basis for plus minus 1 to the 1 and tensorizing it. You define the noise operator by defining it for n equals 1 and tensorizing it. And hyperconductivity is some property which tensorizes. Okay, so if you know it for some domain, that it will also be true for their tensor product. Okay, so there's a general tensorization argument, which is a bit confusing. So I won't do it here, but Ryan Doll found the right way to do it so that it's less confusing, using a two-function version of this hyperconductivity. Yeah, so that's how you prove the general statement. And this general hyperconductivity, it allows tightening all of these applications that we've seen. So you can prove a better level inequality where instead of f2 to the power 3, you get f2 to the power 4 times something polylogarithmic, which is even better. Instead of getting a concentration of 1 over c to the 4, then you get these exponential tails. It gives you, it allows you to prove something called small set expansion that I don't have time to explain. And other things. Yeah, so you don't need it for proving KKL theorem, but you do need it in some other application. Okay, so now you know what hyperconductivity is. So what we're going to do in the remaining 2 days is we're going to cover p-bias analysis. So for analysis with respect to a bias measure, and our motivating application would be this sharp threshold theorem of Bourgain. Okay, so we will look at monotone graph properties. Some of them will have a coarse threshold, and some of them will have a sharp threshold. So I will explain what this means tomorrow. If the threshold is sharp, then it's easier to locate it. And people doing random graphs, they really want to know the threshold. So it's good for them to know that a threshold is sharp. And these sharp threshold theorems, they give criteria for a threshold to be coarse. But if you can prove that this criteria do not hold, then the threshold is sharp. Okay, so the most useful of these is Bourgain's booster theorem, which used to have a Bourgain style proof. So it was a few pages. It was actually an appendix to a paper of Fleetwood. So he looked at the paper as an editor of the journal, I think, and he just said, oh, actually, instead of proving this, you can prove that, and here's the proof. So you can read the proof, and it makes, like, all the lines are correct, but you don't see what's going on. So now we have another proof using this global hyperconductivity, which is a new development, which is actually easy to follow. So it's not due to myself, it's due to Noam Lifshitz and others. And this is what I will present tomorrow and on Friday. Yeah, but that's it for today.